Let us consider some more problems which are related to the equilibrium. It may or may not be the Lame's theorem that is to be applied, but we should be checking whether there are only three forces acting on the body, and so that the particular problem can be solved. For example, there is a problem where one string is attached to the wall. There is a horizontal string also. Some weight is attached at the common point, and now we also know that this cannot be the equilibrium, because if both of them are the strings, then we cannot just hold this string tight unless there is some force which is acting on it. So the figure is given to us, say, in this manner, and the distances are also available. And these distances are 900 millimeters, 220 millimeters, and this force is given as 3:4, and the weight is 120 kg, and the weight is 120 kg. Now if this force is given to us as, say, 100 newtons, we are required to find the tension in AB and AC. So the problem says that find tension in cables AB and BC. Now with our usual consideration, they will be acting in this manner, and this is the angle which we are required to find out, and also angle made by the force. But when we consider this point B, then there is a tension AB, tension BC, weight acting downward, and force, and this problem cannot be solved by Lame's theorem. Here we can draw a diagram, separate diagram, to simplify our task. It is force F given to us as 100 newtons. Weight, it is 120 into 9.81 newtons. This is angle theta 1, which is nothing but tan theta 1. As you look at the diagram, this is theta 1, will be 3/4. Then there will be tension in AB, and there will be tension in BC, and this angle theta 2 can be calculated, because this is again the right angle. It will be 900 upon 220. So tan theta 2 will be 900 upon 220. So all the information is now available, and we can go for the two equations. First, sigma fx equal to 0. Lame's theorem cannot be applied. There are four forces, and you will get it as F cos theta 1 towards right positive minus TAB cos theta 2 towards left negative minus TBC, minus because it is acting in the opposite direction, equal to 0. Weight will not have any component in sigma fx. And in sigma fy equal to 0, you will have F sin theta 1 upward positive plus TAB sin theta 2 upward positive minus W equal to 0. TBC will not come into picture, it is horizontal. Now out of all this data, F is given to us, theta 1 is known, theta 2 is known, and in the second case F, theta 1, theta 2 and W are known. So using the second equation we can find out TAB, which can be substituted in the first equation and then find TBC, and the solution can be obtained. But definitely the problem is not related to Lamy's theorem, because there are in all 4 forces acting at the particular point. If at all we want to convert this problem to Lamy's, if at all this problem is to be converted to Lamy's theorem, then it is possible, because then we can have the parallelogram completed over here and find out the resultant of F and W, which can be very well done, because the two given forces F and W, their resultant can be found out, and then using TAB, TBC and R, the problem can be solved by using Lamy's theorem. Of course, you are required to find out the angle made by the resultant in this parallelogram law. That angle is to be found out, which can be found out through the cosine rule, or you can even use sine rule also. Another way to proceed is I am drawing this F at angle theta 1 and W vertically downward, and I can imagine some force R which is acting at some angle, say alpha, and I say that this system is in equilibrium. Now of course, if you can find R from this by Lamy's theorem, it will be R upon sine of 90 plus theta 1 equal to F upon sine of 90 plus alpha is equal to W upon sine of 180 minus alpha minus theta 1. Now to solve this, we already have value of F, we have value of W, we have theta 1, and R and alpha are the two unknowns. But you will find that none of the ratio is fully calculatable. We cannot calculate the ratio fully, but we can cross multiply and try to get the equations. This denominator is known to us, these two numerators are known, so I can just take first and second, first and third and cross multiply to get the equations as R into sine of 90 plus alpha is equal to F into sine of 90 plus theta 1 as first equation, and R into sine of 180 minus alpha minus theta 1 is equal to W into sine of 90 plus theta 1. Of course, I don't have to go for any formulation over here. Theta 1 itself is known, F is known, W is known. So right hand side can be calculated. Left hand side, it is sine of 90 plus alpha. So it is sine 90 cos alpha plus cos 90 sine alpha. Cos 90 is 0, sine 90 is 1. So this is cos alpha. So you will get R cos alpha equal to some value over here. And this is sine of 180 minus some angle. Sine of 180 minus is sine only. So it will be sine of alpha plus theta 1, and you will get the value. Now these are to be solved. That will create some problem for us. We are interested in finding R as well as alpha. Substituting theta 1 over here, value, and if we expand, we will get it as R sin alpha cos theta 1 plus R cos alpha sin theta 1 is equal to this value. Now of course cos theta 1, sin theta 1 are calculated because theta 1 is known to us. r cos alpha can be substituted from here. That is one choice that we have. And then you will get value of r sin alpha, because this is a numerical value. This value is known to us. Suppose this is value 1. This comes out to be value 2. So this is value 2 only. And here I can substitute this as value 1. So value 1 sin theta 1 equal to value 2. And on the left hand side it is r sin alpha into cos theta 1, say value 3. So I can find out numerically what is value of sin. You can call this as cos theta 1 only. You can find out numerical value of sin r sin alpha, which is say value 3. Now you can square and add V2 and V3 and you can get value of r, and similarly alpha can be calculated. So r over here can be under root of V1 square plus value 3 square. And you can also find out the angle alpha by taking the ratio, because tan alpha in this case will be value 3 upon value 1, and even alpha can be calculated. Now all this job we are doing just to find out the resultant over here, and once that resultant is found out, then we will replace these two forces by the opposite, that is the resultant force, because now these two will vanish. This r alpha is going to balance the resultant of these two, and so if we find this r alpha, we will always get this alpha, so it can be substituted here alpha, and then the diagram will be simply related to TAB, which makes an angle of theta 2, then TBC, and of course R, which makes an angle of alpha, and apply Lame's theorem. Will turn out to be rather a lengthy solution rather than sigma fx and sigma fy. So it's not that we choose some method and that method itself could be wrong. You will have to decide the policy, the sequence in which the problem is solvable. A wrong decision will lead to more time, but it will not result in wrong answer. Choosing the method will play a very important role. I would always suggest that for more than 3 forces, instead of combining the 2 known forces into a single force and then going for Lame's theorem, as I was trying to do over here, combining W and F into a single force, that itself is going to consume more time, and so instead of that, go for sigma fx, sigma fy and find out the tensions in the 2 cables. Problem which is better attempted through sigma fx and sigma fy rather than the combination of Lame's theorem. Consider the next problem. It is given to us that some box of weight 300 kg and its dimensions are also given to us. The dimensions of the block are also given to us as 0.7 meters and 1.2 meters. This is to be lifted by a hook. And for this matter, we are attaching or putting a chain around this particular block. And then lifting it. So there is a chain attached and this is going to be lifted. It is given that the length of this chain is 5 meters. Length of this chain is 5 meters and we are required to find tension in the chain. It's a closed loop of chain. It is actually a loop of the chain of 5 meters length. It is put around that block and the block is lifted using the hook. Now if I name these points as A, B, C, and if I just consider the overall thing, then this is the weight acting downward, which is 300 into 9.81, and if I consider it as overall, then this upward force must be 300 into 9.81, because there will be only two forces, weight acting downward supported by this upward force, and two forces acting on the body will result in equal and opposite forces for equilibrium. And so I can look at point A and I will find that this is the net upward force, which is 300 into 9.81 at point A, and then this is going to be the tension, and as it is a continuous chain, the tension in the chain is going to be a constant one. Now to solve this problem, I will be looking for the angle made by the chain. It is going to be a symmetric one. So if I can find this angle theta, probably my job will be through, because then I can write as this was W. So it is W upon sine of 180 minus 2 theta is equal to T upon sine of 90 plus theta, and the job is done. But for that I require theta, and for finding theta, what they had given us is the length of the chain. Now see, 0.7 meters of the length is wasted on this side, then 1.2 meters, and then 0.7. So ultimately, length of ABC, if we are to calculate, it will be equal to 5 meters, which is total length, minus the length which is around the block. The length which is around the block. And so it will be 5 minus length around the block will be 0.7 plus 1.2 plus 0.7. And so this comes out to be 2.6. So 5 minus 2.6, which will be 2.4 meters. 2.4 meters is the length that is around the block. And so length ABC will come out to be 2.4 meters. Length around the block is 2.6 and the length ABC is 2.4, and therefore length AB, which is same as length AC, will be 1.2 meters. Now once we find that this length is 1.2 meters, if we find that this length is 1.2 meters and this angle is theta, then you can straight away say that either I should be knowing this length or this one. Now due to symmetry, this is 1.2 meters, so this is going to be only 0.6 meters. And so we can write from here cos theta, that is adjacent side upon hypotenuse, is 0.6 upon 1.2, and therefore theta can be calculated. And therefore theta can be calculated, and after substituting that theta, we can find out T. After substituting that theta, we can find out the tension T. Again, the application of Lame's theorem, and even the symmetry has played important role. Now in the same problem, they can ask us as if the block is rotated by 90 degrees and then lifted. Comment whether tension in chain will increase or decrease. So the problem now is having a little twist into it. It is said that the block is rotated by 90 degrees. That means now the block should be considered as 0.7 is this length and this is 1.2. Of course the chain will still go around the block and will be lifted by the hook. Only thing is, now length ABC, as we have written it earlier, this length, that length will turn out to be 5 minus 1.21, then minus 0.7 and minus 1.2. So first of all, this calculation, so it is 2.4 plus 0.7, that is 3.1, and 5 minus 3.1 is 1.9, and therefore length of each part will come out to be 0.95. So this length will come out to be 0.95, and as this is 0.7, this much length will be 0.35, and so theta in this case, cos theta, will come out to be 0.35 upon 0.95, and so the theta is to be used, and then again T is to be calculated, and then we can make a comment as whether the tension will increase or decrease, whether the tension will increase or decrease. So procedurally, the same procedure we will be following. We will be finding out value of T, and then previous value of T and this value of T is to be compared. Procedure remains the same. You will have to find out the length which is in contact with the block, find the free length, divide it into two parts, and then find out the cos theta, we find out theta and proceed further. One of the typical problems we can say. Of course, we can even go further and imagine the case not of the rectangular block, but if it would have been a square block, then there will be one more orientation which will come into picture if the chain goes like this. And in this case the contact changes, diagonal is to be calculated. This type of problem can also be asked. So you can have a square box and then it is rotated through 45 degrees. Even this problem can be attempted. Let the length be 5 meters and the side of the block be 1 meter. And you can calculate, because this will come out to be 1 plus 1 under root, that is root 2, that is 1.414. This is total is 5 meters, contact is 2 meters, so remaining is 3 meters. This is going to be 1.5 meters over here, and this is half, that is 0.72 something. Then you can find out the same theta and proceed with the solution. So these are the variations which can go with a particular block. Another worst case also can come into picture. Even this was simpler. Another case that might be asked is when instead of a rectangular block or box, it can be a circular block, and we are going to attach a chain which is going around this particular circular block, which is to be lifted. Problem over here is we will have to find out the length which is in contact. The total length will be given to us, diameter is also known to us. Say the diameter of this is given to us as phi is equal to 2 meters. Total length is equal to 5 meters. Can it be done? No. Let us reduce this. Phi is 1 meter. Because pi d will be the circumference. If I would have taken it as 2 meters, pi into d, will come out to be 3.14 into 2, 6 meters, and you cannot wound the chain of 5 meters length around it. So I am changing this to 1 meter. So this will be, there will be total circumference of 3 meters. Okay, some length is in contact and some is free length. And you are required to find out the tension. Calculations will play a very important role again. Question is how to find the angle. We are actually interested in this angle. We are actually interested in this angle, but for that we will require this length. To find this length, we will be requiring this angle, say alpha, which is a contact angle. And so problem will proceed more towards the trigonometric solution of the particular figure. So geometric solution that we will be looking for. Information is with us. It's not that we don't have the information, but we are required to find it out. We also know that this length is 0.5 meters. We also know that this is 0.5 meters because it is the radius each. Then using these 2.5 meters and this angle as 90 degrees, we get one important conclusion, that alpha plus theta in this case will turn out to be 90 degrees. If alpha plus theta is 90 degrees, even this angle will be alpha. So many things which will come into picture. And then even this angle will turn out to be theta. Oh, now lot of hint is given to you. You require some way by which the problem can be solved. One of the important problems for Lame is, of course, here it is, hook is attached and it is taken up. Of course, having a lot of difficulty level due to the geometric solution, trigonometric solution. Let us consider some other problem where we are given that there is a pulley which is attached to another pulley. See the construction, one end is attached to the center and the other end is passed over that pulley and will be taken on the other side. This pulley is, of course, is supported and there is some weight which is attached to it. This is tension T. At an angle alpha, and we already have the information about the distances. And those distances are given to us as 2.5 meters and 0.8 meters. Of course, these distances are given to us so that we can find out this angle, say beta. We can find out this angle beta. We are required to find T and alpha. W is given to us. W is given to us as, say, 400 newtons. Of course, tan beta can be written it as 2.5 upon 0.8. Understand the problem. It is asked that find T and alpha, find the tension, and also tell us as at what angle this particular force is to be applied to support the weight of 400 newtons. By geometry we can determine beta, which is tan beta is 2.5 upon 0.8. So beta can be calculated. Remember, it is a single string that is passing over the pulleys, which are always referred to as frictionless pulleys. So there will not be any loss. The force is going to remain same, tension is going to remain same throughout the string. And so even this is going to be tension T, and even this will be tension T, both acting at an angle of beta. And so the free body diagram, or the diagram which is similar to what we call it as the Lamè's diagram, can be drawn in this way. So that these T and T, these are two T, this is T alpha, beta is known to us, alpha is unknown, W is known to us, and T is unknown. And so the equation can be written using Lamè's. We are still bearing with us only two unknowns, T and alpha. So it is W upon sine of 180 minus alpha minus beta, this angle, equal to T upon sine of 90 plus beta, which is equal to 2T upon sine of 90 plus alpha. Out of this, beta is known to us, W is known to us. Aim is to find alpha. It will be better if we consider these two equations, because T will cancel out and you can straight away find out alpha from this. You can straight away find alpha from this. Then that alpha can be substituted and you can use first two equations. Alpha is also known, W is known, this denominator is known, T is the only unknown. You can find out T. So understanding of the problem is very important in this case. Calculations, once the understanding is through, once the procedure is understood, and if we just check whether we are getting all the information, all the values which are required, then we can just write down the steps and then keep on doing the calculations. It is not advantageous or advisable also that you will be doing the thinking job as well as calculations simultaneously. That will lead to more confusion when you actually solve the problems. Instead of that, complete the conceptual sequence for solving the problem and then repeat or continue with the calculations. You can always leave the spaces in between, as I am doing it over here, and then continue with the calculations. At that time you don't have to think, because everything, as whatever you want to calculate, that has already been decided. Now it is just the substitution and the use of the calculator to get the values. Once you assure that you are getting the values, decide the sequence. Go finding for these values one by one, and then you will get the final solution to that particular problem. So that will complete our equilibrium part so far as the concurrent forces are concerned. So in the next lecture we will go for the forces which are not concurrent and the forces are acting on a rigid body. Need not be one or two or three forces like that. There could be multiple forces, and even the reaction will come into picture. And then these forces are again stated to be in equilibrium. Now only sigma fx, sigma fy will not be the sufficient case, because there will be the force which is acting at the offset. So let us have the introduction of that part, and next time we will continue with the actual problem solving. I am talking about some body which is acted upon by the forces which are not concurrent. Say force F1, I have force F2, I might have force F3. Now what can you say about such a body? Even if numerically F1 is equal to F2 plus F3, can you say that this body will be in equilibrium? The answer is no, because these three forces are not concurrent. And if they are not concurrent, then consider the case when a single force is acting onto it. What is the effect? If force F1 is acting, is this body going to shift down only? Answer is no. It will shift down, but it is also likely to rotate. It is also going to rotate. Suppose I hold one of the points. This is made stationary. And if I apply the force F, then this bar is going to get rotated. To prevent this rotation, I apply one more force. So this was F1, this could be F2. And then I find that instead of rotating in this direction, body starts rotating in the opposite direction. And then I will have to adjust this force F2, either reduce its magnitude or increase its magnitude or change its position. One of the better examples that we normally have is when we try to open some nut. So some nut, it is attached to some screw, and if we are to loosen this by the use of spanner, so you could be making use of some spanner. And then you will be trying to open it. Now if you hold it at this point and try to open it, you will require more force than if you hold it away from it. With the lesser force you can apply. Lesser force you can apply and you will try to open this particular nut. This is a common everyday's practice. Like if you are to lift some block by the use of some bar, then we always take the advantage of leverage. We don't put some support over here and try to push it down, because in this case we will require more force. Instead of that we try to put it as close as possible to the actual block and then push this. With little force we can lift this up. Now these are everyday practice things which we are even using in the common world. What we are doing over here is performing the rotation, and rotation is possible because the applied force produces what is known as the moment. Moment in this case is clockwise. In this case it is going to be in this direction. In this case, as I have shown you, one moment, there could be a moment of this force, rotations. And here when I go back to my first problem, then there will be some moment of F1 in this direction, some moment of F3 in opposite direction, some moment of F2 in this direction, and all these moments, they should cancel their effect. Then only the body will be in equilibrium. Though the net vertical force upward is same as net downward vertical force, it does not mean that the body will be in equilibrium. So another thing comes into picture called as the moment, and the question is how to calculate that particular moment. Remember, for the linear motion, it will be the force that comes into picture. That is what the Newton's laws of motion and the initial laws, they talk about the movement of the body in the direction of the force. But the force here that we were talking of was a linear force, and it was a linear movement that will be achieved. Now, when I apply some rotational force which is called as a moment, the body is going to rotate. Suppose this is a bar, then it is going to rotate, and this rotation is nothing but what we call it as the angular displacement, theta. Here if the linear displacement is termed as s, this is going to be the angular displacement. Of course, we are not going for any displacement phenomena because we are into statics right now. But the concept of moment will be the one that is the application of the external force which results in the angular displacement, or will try to rotate the block, rotate the rigid body, and there will be offset which will come into picture. Now moment is also a vector quantity, and if you have some force F, and if you want to find out its moment about some point P, then you are required to simply drop perpendicular onto that force, say R, and the moment, its value will be R into F. It is rather force into perpendicular distance from point about which moment is to be taken. This will be the formula, analytical one. But when we consider it in the vector form, because now what happens is, at point P, due to F, there is going to be a rotation which is going to be clockwise. And by the right hand thumb rule, this vector is actually the one which is going inside the particular plane of this blackboard. If the case is other way around, that the force is like this, and we are required to take moment about this point, then this is perpendicular distance, force into perpendicular distance, this is going to be anti-clockwise, and it is a vector which is coming out. So this is actually a vector quantity, and right hand thumb rule is to be used. Right hand rule is to be used, and the thumb will give us the direction of the moment vector. So in vector notation form, m bar can be written as r bar cross f bar. It is rotation of r bar vector to match with f bar, and that rotation gives us the direction. This is a vector formula, whereas what we are using is rather a scalar notion of it, or the analytical one, by which the moment can be calculated. So moment is nothing but force into perpendicular distance. Now if I consider a case where the force is acting at some angle, say theta, with horizontal, so we have x and y axis, and we want to take moment of this force about origin. This is point P, say x1, y1, at which the force is applied. Now I will have to go for again some mathematical calculation, because I want to drop perpendicular from here onto this line, onto the line of action of the force. And then this perpendicular distance into the force, this perpendicular may or may not be directly present on the force, but it should be on the line of action of that force, and I will get a moment. Now this is going to be a very complicated type of calculation, but instead of that, I can very well consider the case, same problem I am drawing again. I had this F with me, which makes an angle theta, so I will have its horizontal component as F cos theta, and a vertical component F sin theta. And now this F is actually divided into two components. This is the point of application, x1, y1. Now with this, the problem will become simpler rather than the earlier one, because I already know as how to resolve the forces into the components. And now as the coordinates are x1, y1, when I consider this vertically downward force, then I can say a vertical force into horizontal distance. Of course this is perpendicular, so I can have moment about O as F sin theta, that is a force, into perpendicular distance. In this case it will be x1, because it will be the distance measured along x-axis at the point of application. We are simply dropping a perpendicular. So vertical force into horizontal distance, and the horizontal force F cos theta into the vertical distance, because if this is the line of action of that horizontal force, this is the distance under consideration, which will be y1. And now of course for the moment the direction is to be considered as we are considering towards right as positive for the horizontal force and towards left as negative. I will say that the clockwise moment is positive. And now how to check which one is clockwise? See, for f sin theta the force can be taken down, and if you move from origin to the force along the perpendicular line and then move in the direction of the force, then you will get the rotation effect which is clockwise, so this is positive moment. And similarly over here, if you move along the perpendicular line and then along the force, it is going to give us again a clockwise moment. This will come out to be entirely the clockwise moment about origin. So though the definition of the moment is force into perpendicular distance, probably we will deal with it in a simpler manner because we can divide that force into components, and it is a horizontal force into vertical distance and a vertical force into horizontal distance. That should be the criteria. Now one of the common mistake that anybody will commit over here, let me point out that mistake, because f sin theta component over here comes out to be negative. It is in the downward direction, and if you carry with this particular negative sign over here, then you are likely to make the mistake, because then that moment will come out to be negative moment, which should not happen. And so when you are going to use these components over here, use their numerical values, that is all positive. Forget about their directions, whether it is towards left or towards right, towards up or towards down. That particular direction sense which we are giving by attaching the negative sign to it, that should be forgotten, and then the moment should be taken. So you will be never considering f sin theta as negative, though the component of force F is negative. The vertical component of F is negative, horizontal component is positive, but when you take the moment, you should be forgetting that f sin theta is negative. Consider the numerical value of that particular force, take the perpendicular distance, find the product which is the moment, and then check whether it is clockwise, then it is positive. If it is anti-clockwise, it will be negative, and the job can be done correctly. So this was the very base that we will be requiring for our next topic, which is related to the equilibrium of rigid bodies, where the forces are not the concurrent forces. And if they are not concurrent, if there is offset, then these forces will also result in the rotation in that particular rigid body, and even that rotation should be prevented. The angular displacement should be prevented, and then only the body will be in equilibrium. So only the two conditions, that is translation along x is to be prevented, sigma forces along horizontal direction should be 0, and sigma forces along the vertical direction should be 0. Only those two considerations are not sufficient. You will have to also say that the body should not result in any angular displacement, either clockwise or anti-clockwise, but it is a single equation that we will be considering, that is sigma moment about a point should be 0. Now this will also lead to some confusion. That means we are saying that if the moment of the forces about one point is 0, that means that point is not going to move, or that point will be stationary. It is not the case. That means it is not going to rotate about that point. Actually, sigma moment about any point of that particular rigid body will turn out to be 0. If you follow this condition for equilibrium, moment about one point is 0, then you choose any other point, the moment will still come out to be 0, provided that the earlier two conditions, that is sigma fx equal to 0 and sigma fy equal to 0, have already been satisfied. Otherwise it is possible that there could be some, take a simple example. I have a rigid body which is acted upon by some force over here, and if I consider moment about the same point, then the perpendicular distance is 0 and there will be no moment. But then if I consider this point, there will be moment. Now what is going wrong? You have not tested for sigma fy to be equal to 0. If sigma fy is 0, then this will never be the case that moment at one point is 0 and at some other point it will not be 0. So for equilibrium, the third condition now will come into picture, is some of the moments of all the external forces about any point of that particular rigid body will be 0. And as we are introducing the third equation, probably the problems that we are going to solve from this point onwards might contain 3 unknowns and of course their combinations. It will be the external forces acting on the rigid body. There could be some support, and that support might result in the reaction, and that reaction is again going to be the external force. And so all the external forces, that is the applied forces as well as the reactive forces, are to be considered. Sigma Fx should turn out to be 0, sigma Fy should be 0, and sigma moment should come out to be 0. And then using these equations we will proceed to find out the unknowns, that is the solution of the particular problem. So we will start with the equilibrium of the rigid bodies in the next lecture.